of these rules, we will have correctness to some extent. And here I use correctness in a very sloppy way when I'm talking about particular properties you may be interested in. For example, lack of race conditions, lack of deadlock, no crashing your program, null pointer exceptions, that sort of sense of correctness. So our idea here is that we give the semantics of these rules in terms of a low-level system that is then proof sound. And this gives us our reuse of the proofs. The soundness of the low-level system is able to be reused in the proof of correctness at the higher level. And now when you look at yes. Proving that if you follow the rules, you will get correctness is difficult. So maybe I'm saying something rather simple there. So yeah. So my second level is going to talk about a more low-level system. If you want to show correctness with respect to a memory model, we want to show that we don't have race conditions, then we're going to have to look at the happens before relationships, which is a relationship among events happening on multiple threads, perhaps on a machine with multiple cores, etc. Looking at this is complicated. Again, this shouldn't be a big surprise to people here. And so what we've provided is a model that allows us to simulate the happens before relationship while you're executing your program. So this is a model of the execution. So it's one of these low-level models like classic JVM, which looks at reading line fields and synchronization and accessing volatile fields, but it encodes the execution in such a way that the happens before relationship is modeled sufficiently that if we show it works according to this system, we will also have the happens before relationship correct. So that was a little bit fuzzy, but I'm going to show that we have a system that has that. Sort of the vague picture here is that this is our ideal system here, that we have an application programmer working at a high level with respect to a type system. And the programmer is following rules of the type system, and then the type system is proved sound with respect to an intermediate low-level permission system, receptive permission logic or something of that nature, where the programmer is insulated from the permission model. This is the ideal we're looking at, the proof reuse idea, so that the correctness of the type system with respect to the permission model can be completely reused, and in other words, the programmer can be oblivious of these lower levels. And then we want to show that the permission model is sound with respect to a machine model, which insulates us from the actual machine. So this is an ideal with respect to some requirements you may have for your programming system. So there may be other reasons you may not want to follow this, which is fine. That is actually, I see. So an ideal is if we have a system where the type system is not sufficient to show correctness of your program. In order to reason about the correctness of your program, you need to not just look at the type system, but you may need to consider the permission model underneath, or even the machine model underneath that. So you can think of this as sort of an eruption of the magma coming from underneath that is now visible to the programmer. The programmer needs to worry about the machine model, needs to worry about the permission model in order to make sure the program is working correct. And even further, we could excuse me. I got my mouse on the wrong window. All right, where's my mouse gone? There. There we are. Sorry. So even less than ideal is when the machine itself interposes into the situation, and we have the problem of non-portability. Our program now works different on different machines. So this is the vague. I don't want to use the word vague. This is the general idea that I'm trying to propose here. So let's look at the example on the first one. I propose this model of fractional permissions with nesting Fractions allow us to specify read permissions as opposed to write permissions. That's the access part. The nesting gives us the concept of hierarchy, which can express ownership ideas. And then we have the idea of invariants, which are propositions that are going to be true about state of the program as long as you have permission to access that program, that state. If you have permission to access it, the invariant will be true. If you don't have permission to access it, you shouldn't be asking about whether it's true or not. So it's very low level, and the ideal here is we hide it with a type system. So the permission model, you need to have permission to a field in order to access it. And then we also model these synchronization. So if you want to synchronize on an object, we need to know that the object's been properly set up so that p.all is nested in the special lock place. And then when you do the synchronization, it either requires that we have proper lock order, so we don't have a deadlock, and then it gives you permission to p.all. And p.all is a ghost field or a model field that doesn't actually have any state in it itself. We'll talk about what it may have. Or it requires that you already have that permission, in which case you get it back, which is the case for a re-entrant lock. If you're re-entering a lock, then as long as you can say, I have the permission, then of course you can lock because you already have it. And then finally, the third rule here is that if you write a volatile field, you need to ensure that the invariant is true for the value you're writing into it. And if you're reading a volatile field, you are allowed to assume that the invariant is true for the value you get out. So this is the low-level permission system. This is what the rules you need to follow. It's very basic. Things it does not have, it does not specify what actually is nested in p.all. That's the permission you get when you do your synchronization. What state is actually protected by that object? The permission model doesn't specify that. So you just get to say what you want to put in there. Anything you want to put, you can. It's fine. The permission model allows you to do it. It doesn't specify what the invariant is for a particular volatile field. You get to specify that yourself. This is, of course, what's done in separation logic as well. The actual signature for methods or functions, that's up to you. You get to decide what you're going to say about the various parameters and returns. All the idea of types, none of that is specified in the permission model. It's this very low-level model, just looking at field reads and writes, and then access to the synchronization. But, and we've proved this, if you follow the rules, the program won't go wrong. It won't write or read a field that's not there. It won't have race conditions. It won't have deadlock. So this is the idea of the permission system then completely insulates you from the machine model. Then on top of that, you can build a type system. So people in the last 20 years have been talking about all sorts of ownership, uniqueness, immutability. I've been doing some of it myself. Read-only, unique write, guarded, raw versus initialized, abstract read permissions. The concepts multiply. The idea is that we want to give these concepts semantics at the permission level. So you have a concept of what read-only means, and you express in the permission system, and that gives it a meaning. And then the idea is that you have various rules for interacting with these things, and you prove, in whichever way you do it, you prove that if you follow those rules, you will then have the, you will then be able to follow the permission rules, and then you get the proof for use kicks in, and you get the soundness restriction that you want. So you don't need to prove progress and preservation for your type system directly. You just show that if you follow the rules, it will also follow the permission rules. So one of my students has defined a non-null analysis on top of this to demonstrate how this works. Non-null is an annotation, and it's given semantics in terms of permissions. Some of the functions are called constructors, and they have a special role to play. A constructor is called in a special way. It doesn't assume the same things other methods do. It initializes the fields. There's certain restrictions on what methods you can call. All of this is done at the level of the non-null type system. The permission system doesn't say anything about it. It's all simply expressed in terms of permissions at the low level, where it's just talking about calling a method with some sort of signature. And then the proof that needs to be constructed then is if the program follows the non-null type rules, then it will be following the permission type rules. And then by reuse, since the permission system is proved sound with respect to a low level, then the type system is proved sound. So this is in progress by the student who has, now that I'm here in Zurich and not in Milwaukee, a little less pressure on him. But a lot of it's been done. So I'm going to talk about some related work here for the first level, and I'm going to miss out lots of things. But I just wanted to point out two methodologies which are taking some of the same ideas, and they have a somewhat different approach, and I want to evaluate them according to this particular ideal. I mean, there's other ideals you could evaluate them with respect to, but the Boogie methodology, the idea is that we have these high-level concepts, the ownership and immutability, are translated down into the Boogie system with a verification condition generator, and then they're verified down at this low level. And with respect to what I'm talking about in this talk, the issue is that there can be leakage that goes back up. So let's say it doesn't verify. How do you express that back to the programmer? And so there's a known problem. I'm not pointing at anything that people don't know, that, okay, you have some results down here at the verification level, and let's say there's a counterexample or some problem noticed. How does that get back to the programmer? And there needs to be some translation, and that can be an issue. So this leakage is the orange or red start coming back up to the programmer. Here at ETH Zurich, there's this separate intermediate language, SIL. And again, there's a nice automatic translation from Chalice, which is used in Microsoft for their Boogie stuff, and also Scala, nice Swiss language, translated down into SIL. And there at the SIL, there's lots of different possibilities. We have some reuse here of verification. There's abstract interpretation, symbolic execution, and other things. But then again, you hit the issue of what if you have problems? And there's the issue, a known issue, about how you handle problems, how they leak back up, and many others. So I'm sure there's going to be time for questions at the end. I'm happy to acknowledge lots of other work people are doing here. So my second example is at the lower level here, where we're talking about looking at the machine model. One of the things I noticed when I was trying to prove correctness in permission system was that there's not many models out there that used volatile. So if you looked at the lightweight models for modeling Java, a lot of them had locks and synchronization, but very few of them had volatile. But volatility is actually a useful concept. Previously, it's considered this is just sort of a way of avoiding checks, and you can just make things volatile to avoid problems. But actually, there are certain idioms that I can give an example that is available at the end of my slides, if people have questions, of where you can do something interesting with volatile that you might not have thought of. And so you want to be able to model this sort of thing at your low level rather than simply saying everything is volatile is just an escape hatch. So what we've done is provided a model of programming at the low level, reading, writing fields, accessing volatile fields, and also looking at synchronization. And it's going to talk about how we track the happens before relationship as a way of simplifying the reasoning you need to do at this level. And this allows us to express correct synchronization. So what we had before, this is before my new fantastic situation here, you need to find your execution semantics that you're going to do your proofs over. So you would have your basic Java, which would model reason writing fields and volatile fields if you had that. Although previous systems omitted that. And then you define your type system that you wanted to show. Let's say you had some ownership system or something on top of that, and you'd show that this type system is then sound with respect to your execution model. And then you need to do an extra proof here that is going to show that the type system prevents races. And this would need to be a separate proof because it needs to involve looking at interactions between lots of different threads. And so with this proof reuse method, if you use our execution semantics, then that's already done. You define your type system with respect to the execution semantics. So you have, and then prove your progress and preservation, as you've done before, your soundness. But since this model already includes the happens before relationship in it, at the execution, you don't need to do this final step here. Proving that it avoids race is not necessary because it's already shown by doing the subject reduction. So the execution semantics doesn't require direct thread interaction. There are previous models to try to handle this sort of thing by saying that here's how we model it, and if ever two threads try to access something at the same time, the whole program stops. And that will allow you to model these sort of safety issues, but it requires a much more complicated model where you're doing a lot of direct thread interaction. So what does correctly synchronized mean? People tend to use that as a synonym for no race conditions, but correctly synchronized has a fairly precise definition that I've all but copied from the Java memory model papers. It's correctly synchronized if and only if, in all sequentially consistent executions, all conflicting accesses, reads and writes to the same field, to non-volatile variables are ordered by happens before edges. There's a lot of interesting things in there. One of the things I find the most interesting is that we only need to consider sequentially consistent executions to determine whether something is correctly synchronized, but then only for correctly synchronized programs can you rely on sequential consistency. This sort of circularity is actually very powerful, but it allows us then, if we come up with a system in which we make sure that all the programs are indeed correctly synchronized, it means that we can use sequential consistency for our machine model. It all comes down to this happens before relationship, which are the events along any particular thread are ordered in the total order that they have there. And then we add these synchronizes with edges. And so if you fork off a thread, you synchronize with the start of that. If you join to a thread, and as many people know, if you can join to any thread you wish, you don't need to join to the one you forked. You have synchronized with the last instruction there. If you release a lock, that will then synchronize with the next person who acquires that lock. And finally, if you write to a volatile field, you synchronize with everyone who reads it afterwards. And so that means you can't ignore volatility if you're going to try to model execution semantics and see if something is correctly synchronized. So very simple here. Here is an example of 5 threads. The first one forks off the second one, and the third and fourth are communicating with respect to synchronization on mutual exclusion lock, the same one. And the last one has some other interactions. And I've noted the points where this forks and joins and writing and reading volatile fields, etc. So the happens before relationship starts with all the execution, the instructions going down here, and the time goes down in these pictures. And then we add these synchronization edges. So when you fork, that joins to the first instruction. Then when you join, you get synchronizes with the last one. And then, of course, the join could be in a completely unrelated thread. If you release a lock, that synchronizes with the next person who acquires it, and so on down through the system. That's all those ones there. Finally, if you write to a volatile field, that synchronizes with anyone who reads it. There's another one. And now finally, if we get a write here, here's a write, and the question is, if we have now a read here, are these two connected according to the happens before edges? Indeed, they are. This shows that we have indeed a connection between these, so this is correctly synchronized. What about a read here? Again, get there. What about a read here? And if you look, you can't get there from here along the happens before relationships. So this is what's called a synchronization error.
And in the Java memory model, it means your program is not correctly synchronized. And then there's a whole lot of interesting issues that happen that we still want the program to function in some way. But for us, we're going to be saying, well, that's an error. You're not supposed to do that. Yes? Yes? Yes, that's, let me see how far I can. This one here. Right. You could have a deadlock with a join, you mean?
I mean, like.
If this one hasn't, this only connects when you actually hit the end of that. So you can join as many as you wish, but join means wait until that thread stops.
Okay,
so you are.
Typical.
It's like thread join from Java, but not from maybe pthread join. Yes, that is true. All the volatiles with respect to each other. I may be wrong there. I thought it was that each one is a separate one.
Yes, then. Yes. So let me look at that. I'm going to check it out.
They changed that in the.
Yes. Okay. So I'm behind the times. Thank you.
It shows why no one can program to acquire.
With what?
This shows why no one can program to acquire.
Oh, yes. So that's going to be interesting. We want to follow up on that. So for now, we'll stay with the old one. Okay. So the semantics we give is we start with a conventional semantics where you have fields and you store them in the heap and then you read them out of the heap. We have a concept of write keys. Every thread knows some keys. If you, these are just a set of integers. And when you do a write, you can generate a new key. And keys are transferred through memory. If you don't have the key, you can't access the field. And this simulates what happens before. If you fork, you pass the keys to the new thread. If you join, you pick them up from the thread. Release will store these keys in the mutex. An acquirer will then get them. And if you write to a volatile field, you'll get those keys. And if you read, you will get all the keys that were put in there. So that may be, I'm just wondering whether that's the global one or not. Anyway. We start with our same diagram as before and consider the happens before relationship there. That's the graph there. But if we do it with write keys, we have a particular write here, and then the write key generated there will be transmitted through to all these places using these individual rules. So it allows us to reason about the happens before without having to build this large graph. We simply know what write keys a thread has. A different field, the cyan field here, writes something, and these write keys are transmitted here. And we have a third example. So this shows writes to separate fields. And so these are all the places that are legally know about the field and can read it at this point. And if you are, like over here, cannot legally access the yellow field. The write key error is if a thread is ready to access a field, either as a reader or write, and the write key for that object is the write key for every field in the whole system. Each one has some integer associated with it, W. And if a thread does not know W, then it blocks. With the semantics, we're able to prove this equivalence between if the program never has a write key error,
then it means the program is correctly synchronized. And that means that the program has no race conditions. And this is a rather nice equivalence here. It allows you to program your type system on whichever one is the most convenient for you to work with. So if you want to use a right key error, which is what we used, you just need to ensure that you have the right keys you need to read anything or write anything, and then the other ones just fall out. You know that therefore you'll have correct synchronization and no race conditions. And we proved all this in 12. The system doesn't guarantee that race conditions any particular race condition will be detected in every run. But that's actually not necessary, because for a static system, or if you're proving correctness, as long as you can show that the program will never have a right key error, then therefore it will perforce be correctly synchronized. You don't need to worry about particular runs, which that's the way race conditions are. I don't give a semantics of incorrectly synchronized programs. The semantics is sequentially consistent, and so if you have an incorrectly synchronized program, it simply just has a fault. We don't model weight. That's something I would like to add. Primitives, dynamic dispatch, all these things don't involve concurrency, so I thought it was safe to leave them out. And very intentionally, there's no type system. Some other systems will say ownership will have built-in ownership at the low-level system, which means it's less useful for other systems. So it doesn't actually have a particular policy. It simply just shows these things. The related work here, of course, we have the Java memory model. I was interested that this Goldilocks detector had something very similar to right keys and actually dynamically detecting races, which is an interesting issue there. You wouldn't actually want to use our system directly to detect. Not only does it not detect all of them, but you don't want to be carrying around these enormously large sets of integers. The C++ memory model in 2008 was proved making a similar sort of connection between correct synchronization and lack of race conditions. So if we want to apply these ideas of proof reuse to a particular system, say Boogie or maybe SIL, one way you can help insulate the programmer from some of these low-level systems is to have pre-approved idioms with an idiom checker. So an idiom will say that as long as you follow these particular rules that are maybe more restrictive than actually fully necessary, but if you follow these rules, then the low-level system is guaranteed to accept what you do. And the advantage here is that it insulates the programmer from the theorem prover, or the verification engine underneath. So if there are certain things you know that this is always going to be safe, you can do it, then you don't need to worry. The programmer doesn't need to worry about getting errors coming back up. And in fact, if you have an idiom checker that checks that you're actually following those rules, then we can save the time and not even bother calling the verification checker on those things. And I was talking with some people here, and Yanis Cassius immediately thought of the idea of using the fact that Scala has very powerful type system with Scala traits, and if you could you can program certain traits in such a way that the use of that trait will guarantee that it's going to be correct at the level the verification checker is doing. If you can show that ahead of time, that the use of this trait will then be sound at the lower level, then the programmer can use that in knowing that they will not get errors at this low level. They'll only get Scala errors, and presumably if they're programming in Scala, they know Scala reasonably well. And also, there's a benefit in runtime, because when you don't need to do the check, that you know is always going to succeed. And so in conclusion, having this separate proof layers allows us to separate the person doing the application program from the things underneath. And this is useful because it allows us to think at the high level what we want to do. And if we have separate proofs, we have separate proof checking, which gives us all the efficiency we know from that. And this separation is aided if you have type systems that are proved sound at any particular level. So for example, the machine model, it proved we had soundness if we didn't have right key errors. That means the permission system only needs to worry about right key errors, and that means the type system only needs to worry about permission errors, which means a programmer only needs to worry about type errors. So I had planned to be the last speaker, and so I thought I could get away with a shorter talk, and so I have plenty of time for questions now.
guarantee.
They should, that is correct, yes.
They have to prove it, and sometimes in some with an underlying model, the type system is sound. It does give you, it does provide this guarantee.
Absolutely, I agree. So what the separation will give the type person is if you can prove the type system sound with respect to the permission model, then you don't need to go all the way down to the red line. So having the permission model there is a benefit if you wish, and we may be
That means that it helps with the portability, that you can copy to another machine model, you only have to prove it with respect to the permission model.
So only the permission model will need to be ported, not the type system.
Any other questions, Alex?
Have you found examples of type systems that don't fit well with the permission model?
Have I found examples of type system don't fit well with the permission model? Yes. The permission model, for example, doesn't handle arrays at all, and that needs to change. So sometimes these are things that indicate that extensions are needed in a permission model. Some of them may indicate things that, well, I'm just not going to handle. And so it just won't be, I won't be able to be the universal to solve all problems. But yeah, that's.
So if I can follow up, so there's this use paper that was a pop-up this year.
Okay.
Lots of clever separation logic people. And it seems, at least conceptually, they're trying to do something a little bit similar, in that they're trying to produce a kind of framework in which you have to check less when you prove soundness of your logic. They did some examples with type systems, but not so many. And so I wonder how that compares with the effort, but also, so Matthew Parkinson and I looked a little bit into how we might be able to use that framework to reprove the soundness of this initialization type system that Peter and I worked on. And it was interesting, but it didn't really work out so well, because somehow the argument was too much about there not existing references anywhere on the stack to certain things, and that didn't fit too well with this kind of separation logic view of partitioning everything over permission. So I don't know, it would be interesting to see if we could maybe use your way instead.
That may suffer from the same problem, because my system tends to be what's called effective uniqueness. It's only, you can have pointers as long as you don't use them. And so it tends to not be strict about you leaving pointers lying around. But it'd be interesting to explore. Yes, I do want to explore. Yes?
Where does this leave, like, the newer concurrency library that we edit in Java 5, like spin logs or the countdown latch or so, where it's not really like the synchronized keyword, but through application and some lower level magic that your program works out correctly. I don't think it translates well into Java memory model, but it's a sort of application level concurrency control. Could you imagine that your model extends to things like that?
I'm not sure about spin locks, but a lot of these things do deal with mutation. Like, for example, the streams library, which is not quite as recent perhaps as that, but a lot of that, the uses of that can be modeled nicely with the permission system. So the lazy answer is some things work well and some things don't. But yes, that would be good to look at. Yes?
Some possibilities we can extend your approach if you have some kind of incorrect synchronized programs like the benign databases.
So benign databases. Yes, that would be interesting to look at. The model here, as I said, had it used sequential consistency underneath, and so then it enforced the happens before relationship. And then if you have benign races, you need to know more about the store order and things like that. So that would be interesting. So again, if someone, and I've seen some work in terms of having a model of, say, total store order, which is a particular memory model that's weaker than sequential consistency, and then if you have an execution model there, and then you can prove correctly with respect to that, and it would work for that. So the whole idea should work, though my particular thing would not be useful.
Okay, so thank you again.